talk about one of the problems that we encountered here. And that was this idea of, and what the ramifications are, of the fact that we can have this interdiffusion coefficient being proportional to the second derivative, and with the second derivative being negative implies that the diffusion coefficient could be negative. And so I want to talk about some of the ramifications of that and how we can address that problem. And so what is the idea of that d tilde is less than 0? So how do we handle this? And that brings up a whole range of interesting problems. And so the first thing we need is an evolution equation for the concentration. And so we know what the flux is. We have an expression for the flux of JB. We know that in this particular frame they're equal and opposite. But we have to somehow get a relationship between the fluxes and the compositions. And one of the ways to do this is you need a conservation law. And this again emphasizes the fact that composition is a conserved variable. And so if you have a volume that looks something like this, where you have a flux of A atoms into the volume. You have an outer normal here, and you have a certain number of A atoms in this volume. And so the number of A atoms in the volume is going to be the integral over the volume of the density of A atoms dV. So it's a conserved quantity, and that means that we can relate the flux of atoms coming in along the surface, along the outside of the domain, to the total number of atoms in here. And so if you took the derivative of this, I guess you should say this implies, it's going to be equal to d by dt. V. And since V is not time dependent, you can pull the derivative in there. So we have the number of A atoms in the structure change by the flux of atoms coming into the domain. And so you can write another expression for dN dt related to the integral along the surface of omega. So this is the surface area, omega, along the interface, along the surface of V. Along the area. Maybe I'll use S here so that we don't get confused. So the minus sign here is chosen such that flow into the domain increases Na. So if you go back to this picture, if the flux is in the opposite direction to the normal is pointing this way. If the flux is opposite, that means that dN dt, that's negative, so the negative sign here will give you to positive dNA dt. And so you equate these two, and you get that the integral dV is going to be equal to minus the integral over the volume over omega ds. And as everyone knows from their elementary calculus, that you can use the divergence theorem to take a volume integral or a surface integral and convert it into a volume integral. And so that means that this thing becomes times the divergence of the flux, dV, which implies that the integral over the volume now, over the volume of has to be equal to 0. You add those two things together, and then for this to be equal to 0, for all possible choices of the volume, right? So you can change the domain to whatever you like. The only way to get this equal to 0 is to make this term equal to 0, and you get the result of the partial of rho a. It's just the divergence of the flux. And this is sometimes called the continuity equation. Continuity equation. And so you can take the expression we had before and write this in terms of mole fractions and use the form of Fick's first law that we had. Zero there. And you'll get that equation there. So that's basically Fick's second law. So most of you have seen this before. There's nothing fancy about this, but let's consider a simple case. I just want to illustrate case where you start off with a composition profile that looks like this. Let's just do this in one dimension just to make life really easy. So you start off with the composition profile that's a sinusoidal perturbation about some average composition. And that's the height, the amplitude of the perturbations. So we're going to say that C Kx. And I'm just going to sketch this here. We're going to make this far more rigorous in a little bit, but I just want to kind of motivate why we're doing the next step actually. And we're going to take D is equal to, going to be D at C0. And you can ask the question why we're going to do that, and you'll see in a second. We can make this quite rigorous, but suffice it to say that if you do that, the equation looks like this, right? And then if you plug that equation into here, on the right hand, this concentration here is a constant, so that disappears. A is a function of time, and so you'll get dA dt sine kx. And on the left-hand side, you'll get d. There's the a will come out because there's no time derivative, and you'll just get a minus kx. And so that gives you dA dt and that's basically what I wanted to get to. Okay, so the reason why I did this kind of to motivate the problem here is if we have this expression that looks like this, you consider the case where d tilde is greater than 0, dA dt is less than 0. And that's the classic diffusion equation, right? Because if I gave you a fluctuation like I show here, Classic diffusion would say that the system would go to a uniform composition, right? If diffusion, however, is negative, if the diffusion coefficient is negative, dA dt is greater than 0. And so that means that this fluctuation here, the amplitude grows. It gets bigger. It gets bigger, okay? And so the system is unstable. It will grow. And it's even worse than that. It's even worse than that because you can see that dA dt goes to infinity as k goes to infinity for d less than 0. And so the smaller the wavelength, or the bigger the wave number, smaller the wavelength, bigger the wave number, the faster the amplification rate. Okay? And so in your laboratory this afternoon, you'll be solving the diffusion equation. And what we'd like you to do is write a code to solve a diffusion equation and then plug in a negative diffusion coefficient and see what happens to your code. And so, and on thinking about the strange results you get from your code, remember that, okay? Remember that. All right, so we have this strange problem here that the amplification rate goes to infinity as dA dt goes to infinity. And this was realized by John Cahn many years ago. There was a problem with the diffusion equation for systems within the spinodal region. And what he was able to do is to use a formulation of thermodynamics that goes back to Cahn and Hilliard. And this is a journal, Chemical Physics, I think, 1958. Last time I checked, has about 7,000 citations. Relatively important paper, as papers go. And basically the idea here is that they want to consider the energy associated with gradients in composition. And that's the idea. This actually goes back to van der Waals, but they were kind of unaware of this when they wrote down their theory. Landau and Lifshitz had something very similar in the physics literature for superconductivity, but they're the people that are kind of credited for basically putting it into the context that we're talking about. And so let me motivate why can gradients in composition change the energy of a system? Okay. Now, so this is different than what classical thermodynamics, right? Everything we did in the first hour was I give you a composition, you have the free energy, right? But here what we're going to say is if I give you a composition, you don't have the free energy until I tell you something about the composition gradient as well. Okay, and so let's consider the following. So let's say you had a composition profile that looked like this. C is a function of x, and this would be your position of interest here, some x0. No, let's actually call it P. This is an argument that basically goes back to Cahn in his spinodal decomposition review paper in MetTrans many years ago. And let's say you have an interaction range here of the atoms. And this is the crucial piece of physics that allows us to say something about composition gradients. And so if you're an atom sitting here, what it says is that unlike this nearest neighbor kind of bond model that we did with a regular solution, you actually can sense the atoms around it a certain distance, around you a certain distance away that's given by this interaction distance. And so in a crystal, you can have interaction ranges maybe on the order of 4 or 5 lattice parameters. In a polymer, because the size of the change is so big, these can be really long-range interactions. Okay. And so if you look at the average composition, in this case, composition at P is equal to the actual composition at P. If you looked at a linear composition profile, exactly linear, so here's your atom sitting at P. This is X. Let's say you had a linear composition profile. So that's your interaction distance again. Here, the average composition equal to the actual composition. At P. But if you have a composition profile that has some curvature in it, so here's your atom at P, and let's say the composition profile looks like this, and here's your interaction distance. The average composition at P is going to be given by a straight line, and that's the average composition. Average. And you can see that the average composition is not equal to the actual composition. And so what it says is that if I give you material of composition exactly equal to that black dot, an atom sitting there in the system with this curvature in the composition profile says that, well, that's not the right composition, because I can kind of sense that the atoms around me are not equal to the average, and that average composition of the atoms around me are not equal to the composition at P. And so what you might expect is that the chemical potential will be somehow proportional to the curvature of the composition plot. Okay? And so the fact that you have if the interaction distance was in fact 0, like you have in the nearest neighbor model that we just did, this effect wouldn't appear. But in real systems, the long-range interactions exist, and so you have this coupling between the curvature and the actual value of the chemical potential at P. Okay? And so the system is surrounded in this case by more atoms that it dislikes than it would be at equilibrium. And so what that means is that the free energy can be a function of composition. This is what I just gave you before. F, I'm using F here because I've gone back to the Cahn-Hilliard Helmholtz free energy, but it really doesn't matter. It can be a function of, let's say, of the gradient in the energy. It can be a function of the second derivative of the free energy, for example. And I want to make sure that everyone understands exactly what I mean by this, is that it says that if I go to a point P and I give you the composition, so here's the composition, you won't know the free energy until I also give you some information about the gradients. Okay? And so what we're going to be talking about here are systems in which these things are viewed as parameters. You know, when you think about composition and the gradients, they're somehow connected, right? So they're smooth profiles. But when we write this energy, what we're thinking about is I give you a composition, and you can actually conceive of doing this, at least in your mind, where you fix the composition, and I say, okay, what is the gradient? And what it's saying is that the energy is going to change depending upon what that gradient is. And so you want to view these gradients here as parameters in the free energy. They're kind of things that you can vary independently from the actual value of the composition at that point. And this is the reason why I emphasize this is that this is a relatively subtle point. And when Cahn and Hilliard first published their paper, there was a group of people, relatively famous material scientists, who didn't quite get this idea and wrote a paper in Acta Materialia, basically criticizing this entire framework, the Tiller, Pound, and Hirth, for example. They thought it had to do something with a Taylor series expansion in space. Completely incorrect. Okay, so you want to view these really as parameters that can vary independently. And so you can write a Taylor expansion in the gradients. And so you can include, if you look at this term here, I mean, you can include fourth derivatives, fifth derivatives, and we're just going to take the most simplest case where we're just going to look at these two first terms here. And so you'd write the free energy function as a function of c and dc dx as some function of c, and 0 plus and I'm not going to worry about symmetries and doing this in 3 dimensions. I just want to kind of get the right ideas across without a lot of complicated algebra. This is the kind of the simplest bargain basement kind of approach. And L is equal to, by the definition of a Taylor series, is the change in the free energy with respect to a gradient. And K is the change in the free energy with respect to the square of the okay? I think you get the ideas now that you're really viewing this as parameters. So it's the change in the L here is exactly as I say. It's the change in the free energy as I change the gradient. This one here is the change in the free energy as I change the square of the gradient. So they're really kind of independent parameters. I'm going to do the simplest kind of argument here about symmetries to kind of give you an idea of why some of these terms in the Taylor series of expansion. In fact, if you look at the Cahn-Hilliard papers, they do it in full 3 dimensions and the generality, complete generality here. But imagine, let's look at this term here. Let's say I have my coordinate system here. Yeah.
Taken the slope, square of slope is also fixed. You can't really make that independent.
Oh, you're worried about this? Yeah, you're right. In fact, what will happen is so this is okay. So this is really kind of like a second order term. It's kind of at the same order as this. Yeah. In fact, oh yeah, that's right. So there'll probably be a half. The half there. Sorry. This or put this term in here. Yeah, you could. You actually could.
That's what we are doing here. We are trying to write the free energy function in terms of its first and second order derivative.
Right. Exactly. That's right. Precisely. Yeah. So you're suggesting that we could put this. Yeah. That's right. That's what you're saying?
Oh no. I mean, can we put their k into d2c by dx2 in the next expression in your?
Oh yeah. So yes, if you include this term.
Yes.
Yeah. So you would have another k1 x squared, and what the reason why I'm not going through this is that you can show that if you include this term and you integrate by parts, you can make it look just like that term. Okay. Yeah. So if you let k1 be a function of composition and you integrate it by parts properly, you can combine those 2 terms.
Or if you check the free energy is a function of first order derivative, second order derivative.
Yeah, I mean, but this thing here can be a function, polynomial in space. Yeah. That's a good question, and really this is a polynomial in the gradients. You want to think about it, a polynomial in the gradients that you're doing a Taylor expansion about, because it's really not a Taylor expansion in space. That's really an important point. Yeah. Okay. So I'm looking at the first order term here. So L, the C is a function of x. And the interesting thing about this is that if you put down your coordinate axes in your crystal, so here's your crystal. If you put your coordinate axes down like this, the sign of that term changes, right? With respect to the charge. It changes when you go from x to minus x. And when you think about it, the free energy shouldn't be a function of how you put down your coordinate system, right? And so L has to be equal to 0. And in general, what that means is that for a non-centrosymmetric crystal, for a centrosymmetric crystal, there are some crystals that don't obey that symmetry, but we're going to neglect them. We're just going to be worried about more simple cases here. And so you end up with a free energy that looks like that. And F here is a free energy per volume. Free energy per volume, which means that the total free energy of the system now is equal to the integral of the volume dV. Okay. Now we're facing an interesting problem: is what is the equilibrium state? So what is the equilibrium in the system? And so for those of you who haven't seen this before, we're asking something very different than what we've done before. So remember when I looked at when we had this the energy, right? So here, what we say, well, the system is at equilibrium where the chemical potentials are constant in the system, right? For the case of composition. Then we said, well, if you have an ordering system, the system's in equilibrium when the first derivative of the energy with respect to the order parameter is equal to 0, okay? And so what we're asking, for example, in this case, is to identify the values of the order parameter where the system is at its minimum. You go back to what we're doing here, and we're going to ask a different question. And the question here is not what is the value of C that minimizes this free energy or extremizes this free energy. We're going to ask what is the function of C that minimizes this free energy. Okay, so we're asking something, going to ask something very much more general. It says what is the equilibrium in the system? In other words, what is the value that extremizes Ft? So in other words, we're looking for a function. And basically, we're going to be taking a functional derivative. Derivative of the equation and set that equal to 0. And so I'm going to do this in one dimension, just to make life easy. And so you have the total free energy is given by the area of an interface, say, times the integral from x1 to x2. F is a function of C plus K and since this is so important, actually, I'm going to go through the details here so that you understand clearly what's going on. And so what we're going to do is we're going to set the first variation of the energy, or the functional derivative, first variation of the energy. We have to find that. And we're going to set that equal to 0. Okay, so this is this functional derivative, or delta. Works all the time. You always get the right answer here, regardless of how complicated your energy function is. And so you pull delta through, and so it's a function of c, and so you get the first variation, the derivative of f with respect to c times the variation. And so you literally want to think about this as in terms of going into the system and changing the concentration a little bit at one point, and asking the question, how much does the free energy of the system change if I change the composition at a point by a little bit, right? And it kind of makes sense. You take the derivative of f with respect to c, multiply it by that small change. Kind of makes sense. But the difference between that and a derivative, we're going to say that the gradient energy coefficient, this k, which measures the effects of the gradients on the system, is a constant. And so you have operating on dc dx. And so you can write this as a variation in c plus k, 2k, times the variation of the derivative. Okay? And so now think about what these two terms mean. So you have this term, which is the variation of the concentration, and this one, which is the variation of the derivative of the concentration. So again, it's kind of the same thing, right? So I can vary the concentration derivative and the concentration. But now that we're looking for c as a function of x, these two variations are not independent. These are not independent. They're not independent. In fact, the variation in c is related somehow to the variation in dc dx, because if you start off with a uniform concentration, and you change the concentration a little bit, you introduce gradients, obviously, right? And so they're not independent. And so you have to relate independent. And so you have to relate one to the other. And so let's just consider the term, the second term here. Let's just consider the second term. Second term. 2k times the integral dx. And so we're just going to integrate by parts. Term by parts. Right, so that's the formula for integration by parts. And basically, oh well, you'll see. Okay, and so what we'll do is we'll say that dv is going to be equal to d by dx x. That implies v is going to be equal to delta c. Yep. And u is equal to the dc dx. That implies that du is going to be equal to dc dx. And that implies that 2k times the integral dc dx to be u times v, which would be minus the integral of v du, which is just dx times 2k. Okay. So let's look at this expression here. So we have these terms here. And what they are is that they're terms that basically go out to the boundaries. And so they tell you something about how gradient terms, here you have the gradient energy coefficient, affect concentration gradients at x1 and x2. And so if you're doing things like spinodal decomposition in finite sizes, finite domains, or anything associated with the surface, these terms are very important. And I don't know how many papers I've reviewed where people forget about these terms and then use standard flux conditions, for example, at boundaries. So because what we're going to do is we're going to say we have an infinite system, we're going to neglect these, okay? So we're going to say that in infinity, dc dx equals 0, plus or minus, or plus or minus infinity. So we're just basically going to neglect those terms. And so you can write this as, but you have to keep in mind that when you do interfaces, or when you do surfaces, you have to include those terms. You can't neglect them like what we do in the classical theory of spinodal decomposition. Okay, and so now we can put this back into the integral of what we had before to get the first variation of the energy is going to be equal to the area to x2 times c minus 2k dx. Okay? So remember I said over here that these things are not independent. And basically what you're doing here is when you integrate by parts, you can expose the variation of this gradient with respect to position. So it basically allows you to expose this thing. Bring the two things together, and you have this out here. Okay, and so we're going to look for equilibrium. Implies that delta ft has to be equal to 0. And so you can make this, okay, so here's kind of an important assumption here. So again, you want to think about this in a physical way, kind of not a mathematical way. You want to think about this as going into the system and changing delta c someplace as a function of position. It's pretty clear that for a particular value of delta c as a function of position, and for a particular value of this thing, you can make this integral equal to 0. But if you wanted to do it for the most general case for any delta c that's reasonable, that's not discontinuous or something like this, for any reasonable delta c, the only way to make this thing equal to 0 is to set the term in the brackets equal to 0. Okay? And so you want to set the term in the brackets equal to 0, and that means that at equilibrium, you have 0 is going to be equal to the partial of f dx squared. And this term here is sometimes called an Euler-Lagrange equation. Sometimes called the Euler-Lagrange equation. And you will also see it sometimes abbreviated in the community, in the phase field community, is that they don't bother writing Euler-Lagrange equation, but they use these delta signs for the first variation of f with respect to c. So they kind of go over to here and they divide by delta c, and they kind of use this as a shorthand for the Euler-Lagrange equation. So you'll see this in the literature quite often, and we'll be using this as we go forward. Okay, so this is an equation for c as a function of x. And so the prescription here is that if I wanted to look for at equilibrium, I'd solve this equation. It would give me c as a function of x, and then I go back to here, and I plug in c as a function of x, and I get the energy. Okay? There's a minor problem here, is that if you look at this equation, there's no constraint on the average value of C. In other words, if you wrote this in terms of order parameters, it would be exactly this. Equals 0. And you'd be free to change the value of the order parameter any way you'd like to make that equal to 0. You could just basically, for example, in the system I just gave you, in this case here, well, the equilibrium would be down here at the bottoms. All right, and you look at this equation here, so that would be equal to 0. And the way to get equilibrium would be say that's equal to 0. In other words, the order parameter's uniform at equilibrium. Okay, and you could do that with an order parameter, but for composition you have the problem that, wait a minute, I have two phases. I can't make the composition uniform every place because I have a conservation. Okay, and what that means is that when we derived this equation in terms of composition, we left out a constraint, and that constraint is one on the average composition. So this is perfectly okay for an order-disorder transformation. It's not so good for composition. To conserve the total of A atoms. And so what that means is that you need to put in a constraint equals 0. And C0 is the alloy composition. Is the alloy composition. Okay? And so you're basically saying that you can have any type of fluctuation, but only those fluctuations that conserve the overall number of atoms is allowed. Okay? And the way you add a constraint to a free energy functional is using Lagrange multipliers. And so you multiply this by lambda, and you subtract from the free energy functional I had before. Subtract or add, it doesn't matter. The sign of lambda just changes the sign of lambda. And now we're just going to subtract off that term, dx. And those are, you go through the same thing, and so you set the first variation of that equal to 0. And you have the first variation of the term that we did before. Plus, minus times the first variation of C0 dx. The first variation of C0 is 0 because it's a constant, right? And then you have just the variation in C. And so that you collect the terms and you get dx. And that implies that if you set this equal to 0, you get lambda is going to be equal to the, hold a second, wait a minute, sorry. Write that. Take the, once you go back to what we did before, and this was that. And lambda is a constant. And this is the thing that's uniform at equilibrium. Okay, and so let me stop here and talk about the physics a little bit, not just the mathematics here. Okay, so let's go back to the when we first started the problem. We had the double well free energy, and I said the thing that's uniform at equilibrium is the chemical potential mu, right? Here, what we found is that when you have a gradient energy coefficient, a non-zero gradient energy coefficient, the thing that's uniform at equilibrium is not the chemical potential, mu, that we've seen before, but it's lambda, because lambda is a Lagrange multiplier. And so sometimes you'll see this called a generalized chemical potential in the literature. And it's because it includes a term that looks like dF/dC, which looks like some chemical potential terms, but it has this gradient term, okay? The term involving the second derivative. Remember when I gave this argument about whether gradients should be important? Remember I said that if there's some curvature in the free energy, if there's some curvature in the composition, it should change the chemical potential? Curvature in the composition. And so, Feynman had this famous line that if a good physicist can determine the answer without doing any mathematics, and here's the mathematics. So John Cahn knew this was going to be the answer before he did the calculation. So the Euler-Lagrange equation gives you the curvature and says that the chemical potential is a function of the curvature in the composition profile. Okay. And so this is what we're going to be using to describe the evolution of composition in materials. And it's basically the basic model, the simplest model for a phase field model. And so let me try to make the connection here, right? Remember, we had an equation for the flux in the absence of a gradient energy coefficient that looked like M, where M is I think we wrote it in A and B and not component 1 and 2, sorry. CA-MB plus MB-CA, right? So M is this weighted average of the mobilities of the two components. And we call this the diffusion potential. And it was in this it's difference in chemical potentials because we're in this volume-centered frame. In our case, we're going to have lambda, which it's uniform at equilibrium. At equilibrium. And that implies that the flux is going to be equal to minus m times a gradient in lambda, or the gradient and so let's just look at this term here. Right, so that's the definition of the free energy. And rho here is volume. And if you let C be equal to CA, that implies that the partial of F with respect to C is going to be equal to mu A minus mu B. And so that means that if you yeah, okay, I'm sorry, I'm going a little bit faster. So if you take this equation here, take the derivative of F with respect to CA, and you use the Gibbs-Duhem equation, you come up with this equation here. And you can see that this term here is exactly this. Exactly this. And so you basically have recovered the classic diffusion equation written in this volume-centered frame plus a correction term due to the gradient energy coefficient. And so that means that you can, that the assumption is that J tilde, lambda is written in the, centered frame, which implies that the vacancies are always at equilibrium. Okay? And so we're going to derive tomorrow the Cahn-Hilliard equation. And so embedded in that Cahn-Hilliard equation is the assumption that the vacancies are always at equilibrium. And the reason why that's important is that if you have evolution of the system, or if you have fluxes that are in systems where the vacancies are not at equilibrium, and so for example, the way vacancies become to equilibrium is that you have climbable dislocations. And so if the spacing between the climbable dislocations is large compared to the size scale of the phase separation, the classic Cahn-Hilliard equation doesn't work. Okay, so you have to keep in mind that this is an assumption that we're going to be using for the Cahn-Hilliard equation. And so what that means finally is that the flux can be written as minus m times, if you wrote it in 2 dimensions, times the Laplacian of the composition profile. If you use the mass conservation, the partial Cj, you end up with this thing that looks like and this is called the Cahn-Hilliard equation. Cahn-Hilliard equation. So it involves the compositions that you get from the free energies. And so here's the connection to thermodynamics. So I give you a free energy function. It can be something that you get from a Calfad fit, for example. Calfad free energy function is a function of composition for a particular system of interest. And if you know what the gradient energy coefficient is, you just have to take the Laplacian of the concentration field and you get the flux. Okay? And so tomorrow we'll be talking a lot about this equation because basically what it does, it is the basic model. If you look at any phase field model, it starts with one of these kind of Cahn-Hilliard-like equations. Okay, questions? Oh, the interaction range? You know this argument here? Yeah. So if you look at a point P, that gives you the concentration. So let's say you wanted to evaluate the free energy as a function of the concentration. So at point P, you'd get the concentration, right? And then you'd plug it into your free energy function. I was using GM. And you get the free energy. And what this says is that this is not the full story because the composition of interest really isn't this one, but it's some sort of volume averaged composition that sits up here. And so the system senses the fact that in this interaction range, the average composition in the interaction range is not actually equal to the pointwise composition there. And so this average, this distance here, or the fact that it's an average and the fact that there's a difference means that the curvature will affect the chemical potential. And this has an interesting story, by the way. I mean, so it says, if you think about it, that you have to have long-range interactions or interactions over a distance p that's on the scale of multiple lattice parameters for this model to work. And there's a relatively controversial issue in the community about why, as you'll see in a second tomorrow, why the linear theory for spinel decomposition has never been seen in metals, where it has been in in polymers. And the reason one reason that people think is the case is that in metals, this interaction range is so short, whereas in polymers, it's so large that it's behaving more like a quote-unquote mean field model. And so this is kind of this idea of interaction ranges is embedded in everything that we've done. I mean, and you can ask lots of questions about these interaction ranges. Well, there are other terms in this Taylor series expansion that I've left out. Are they consistent with the interaction range that I put in here? So there's lots of very deep questions about how you integrate this with the Taylor expansion. We were talking about how many terms in this Taylor expansion do we want to put in. And it's kind of an interesting and deep question about how you formulate these kind of models. So that's an important question about the physics of these problems. Other questions? Okay, so in your exercise this afternoon, you'll be actually solving the diffusion equation, and because I think, as you can see, that the diffusion equation basically is this part here that basically comes into play in solving the Cahn-Hilliard equation. So it's like the first step in the analysis of the phase field equations. Okay, very good. So I'll see you tomorrow morning, right? Same time, same place. Okay.